All right, let's pull back the curtain on the invisible math that, and this is no exaggeration, powers literally everything you use. I'm talking about your phone, your car, the entire city power grid. It all runs on just a few really elegant and powerful rules.
You know that feeling when you look at a complex circuit board and it just looks like a maze? Or maybe you've wondered why using a super thin extension cord for a powerful space heater is a really bad idea. Well, the answer isn't magic, it's math.
And today, we're going to decode 4 of the absolute foundational concepts that engineers use to take that electronic chaos and turn it into perfect working order. You ready? Let's jump in.
First up, let's talk about the wires themselves. See, you can't just grab any old piece of metal. If a wire is too thin for the amount of electricity or current that's flowing through it, it's going to overheat and could become a huge fire hazard. So engineers needed a super simple, standard way to measure a wire's thickness.
And to do that, they came up with this really clever unit called the circular mill. Now, a circular mill is just the area of a circle that has a diameter of exactly 1 mil. It's a unit that was custom built for one job and one job only, measuring round wires.
So, how small are we talking with 1 mil? Well, it's tiny. 1 mil is just 1/1000th of an inch. We are dealing with incredibly precise measurements here, and they're absolutely critical for both safety and for efficiency. But here's the genius part. To find the area of a wire in circular mills, you just take its diameter in mils and you square it. That is it. No calculators, no messing around with pi. It's a brilliant little shortcut that makes one of the most common calculations in electronics way easier. Okay, so let's move on to our next secret. If you've ever popped open an electronic device, you've definitely seen these tiny little components with colored stripes on them. They're called resistors, and their job is to control the flow of electricity. But how in the world do you know their value just by looking? Well, you learn to read the rainbow. So there's this classic little phrase to help you remember the code. Better be right or your great big venture goes wrong. Each color, from black to white, maps to a number, 0 through 9. This chart right here is basically your secret decoder ring for every resistor you'll ever find. And here's how you actually read the bands. The first 2 colored bands give you the first 2 digits of the number. Simple enough? The third band, that's your multiplier. It just tells you how many zeros you need to add to the end. And that last band, usually gold or silver, tells you the tolerance, which is just how precise that resistor's value actually is. All right, so now we've got our components. How do we actually connect them? Well, it turns out there are 2 fundamental ways to do it, and you can think of them as the basic grammar of the language of electronics. You've got series and you've got parallel connections. In a series circuit, everything is connected end to end, kind of like a one-lane road. This means there's only one path for the electricity to flow, so the current is the same everywhere. But in a parallel circuit, the components are connected across the same 2 points, creating multiple paths, like a highway with many lanes. In this case, the voltage is the same across each lane, but the current gets to split up. They're 2 opposite but equally important ways to build things.
And I'm serious here. Every single electronic device, I don't care if it's a flashlight or a supercomputer, is really just a complex combination of these 2 simple connections. If you understand this, you understand everything.
Okay, but what happens when circuits get really complicated? You know, with dozens of parts all mixed up and weird combinations of series and parallel? Well, you need a system. You need a reliable way to analyze them. And that brings us to our first major league technique, mesh analysis, which you can just think of as the loop method.
So, mesh analysis is this powerful procedure for figuring out the current anywhere in a circuit. It's all built on a fundamental rule called Kirchhoff's voltage law. All that law really says is that in any closed loop of a circuit, all the voltage you gain has to be lost. You can't just create or destroy energy. It all has to balance out. The process itself is just incredibly systematic. First, you find all the individual loops, or meshes, in your circuit. Then you write one equation for each of those loops based on Kirchhoff's law. And finally, you solve that whole system of equations to find every single unknown current. It basically turns a crazy puzzle into a straightforward algebra problem.
But what if you don't really care about the current? What if you're more interested in the voltage at different points? Well, there's another tool for that. Think of it as the cousin to mesh analysis. It's called nodal analysis, or the junction method.
Nodal analysis focuses on the nodes. Those are just the points where different components connect to each other. It uses Kirchhoff's other law, his current law. And that law is based on a really simple idea.
Whatever electricity flows into a junction has to flow back out. Current can't just appear or disappear into thin air.
And just like before, the process is super methodical. You pick one spot to be your ground, or 0-volt reference point, then you write an equation for every other junction based on Kirchhoff's current law. You solve those equations, and boom, you know the exact voltage at every single point in your circuit. So, which one do you use, mesh or nodal? Well, the engineer's secret is all about efficiency. It's about working smarter, not harder. You look at the circuit and you pick the method that gives you fewer equations to solve. Sometimes that's the loops, sometimes that's the nodes. They're like two different languages that describe the exact same thing, and a real expert knows which one to use and when.
Okay, so let's wrap this all up. What we've just covered. These aren't just random facts. This is the essential toolkit that every single electrical engineer uses to make sense of the totally invisible world of electricity.
Think about it. You now get how to size a wire with circular mills so it doesn't burn down your house. You can look at a resistor and decode its value from the colors. You know the fundamental grammar of all circuits, series and parallel. And you've got the two heavy hitters, mesh and nodal analysis, to solve for any voltage or current you could possibly want.
These concepts are the bedrock that all of modern technology is built on. This is way more than just math. It's a language for creation. So the next time you look at a circuit board, you're not going to see a maze anymore. You'll see a language. And now that you know a few of the words, what could you build?